If you see a symbol, E with a degree sign, that is the standard reduction potential. Where's the E in all of that? Well, it's electromotive force, which is a term that gets used, and then of course we promptly forget it too. It's not any better than standard reduction potential in describing things to all of us. But it was always going to refer to a reduction half reaction. So this is what you're going to find when you look in the tables in the back. The reactants and products should be in standard states at 25 degrees Celsius, because apparently electrochemical people really like to be in warm rooms. Dissolved substances, standard. Standard is 1 molar concentration. Gases at 1 atmosphere of pressure, again, standard. So these are all referring to if we were doing the measurements in these conditions. So the standard cell potential. How's that different? Well, the word is different. Cell instead of reduction. Oh, it's for the whole cell, not just a half reaction. So the complete reaction includes a reduction and an oxidation. That came from a standard reduction potential. Okay, reduction, red cats, right? Okay, so the reduction potential of the cathode minus the one at the anode, because the one at the anode is actually flipped, right? It's not a reduction, it's an oxidation, so minus. That's what's going on there. EMF, electromotive force. We generally just refer to it as voltage. We're rather lazy about that. We use voltage, and the unit is the volt, not the joule. If you see these words, voltaic cell, galvanic cell, you know, it's much easier just for you to think of the word battery because you're used to batteries. And chemical energy is transformed into electrical work in a spontaneous redox reaction that occurs when you complete the circuit. As soon as you turn the circuit on, completing the circuit, it's going to start doing the business of changing the chemicals into electrical work. And if you see the word electrochemical cell instead of voltaic or galvanic, you should think rechargeable battery, because if it's an electrochemical cell, you can push it back the other way. You can either take the chemical energy and make it into work, or you can push it back the other way. If you supply a higher voltage to it, you can push that redox reaction in reverse. It is an equilibrium, and you can just raise one end and push it back the other way. And here is a nice little example where you have some sort of a multimeter so that you're measuring what the voltage is. We're taking our friend here with the zinc and the copper, and we're saying, well, what is the overall voltage that we're going to measure? And what we end up doing is going and looking up what is the number that's associated with the cathode and subtracting the number that's associated with the anode. And so there's the two things that you come up with when you go look up. They're both in the chart as reduction potentials, right? But we're going to have this minus sign to turn this one around, right? So there you see, there's this one, and then we're turning around the number that we looked up, and overall we'll get this number, which is what we should expect to measure if this was 1 molar and that was 1 molar and the temperature in the room was the proper temperature, and we're operating at 1 atmosphere of pressure outside of it. So when you're doing this, because you're looking them up and they're both reduction potentials, you have to remember to do this in such a way that you're going to end up with a positive number. You're going to look at the two numbers and you're going to pick the one that is the most positive and say, that's the cathode. And then the other one will be the anode, and you will subtract it. So you see, they both could have been positive numbers if we'd used something instead of zinc. And then you would say, well, which one is most positive? That will be the cathode, and the other one would be the anode, so that you always want this E cell to be a positive number. If you have a negative number, it's because you've gotten which one is the anode and which is the cathode mixed up. Here's another wonderful battery, the Zinc-Air Battery. There's 2 half reactions. We go and we look them up. Here's the zinc oxide turning into pure zinc, and there's a voltage associated with that. It's negative. And here's, well, it's air. What's part of the air? Well, as it turns out, I see this as zinc oxide as opposed to zinc. So the part of the air I'm interested in is actually the oxygen in the air. And if I go look this up, I find out that it's 0.401 volts. That means that I'm going to look at these two and say, well, I do believe that is going to have to be the cathode. The 0.401 has to be the cathode because it's more positive than this is. When I turn this into being an anode, that would be like saying, oh, got to flip the whole thing around, right? And that is what has happened between here and here. Flipped it so that the solid zinc is now on the left instead of the right. The other thing that had to happen is that this zinc one had to be doubled because of the fact this had 4 electrons, this only had 2. So everything had to be doubled within the equation. So this is minus a minus becomes a plus, and you get 1.65 volts out of this. And if you start adding all this up, you see that the electrons are going to cancel, the hydroxide cancels, even the water ends up canceling, and you're just left with this as the reaction overall. A lot of stuff going on inside the battery that we don't pay much attention to until we start studying this chapter. Now, did you notice we didn't double the voltage? Well, we can say these pretty words, that this is an intensive property. It doesn't depend on the amount of the substance. That voltage is the same no matter the size of the battery. The amount of the work done depends on 2 things, what the voltage is and how many electrons are going through it. And the number of electrons is going to be determined by the amount of materials. I'd like to clarify this just a little bit by talking about something you're probably a little more familiar with from physics. And that is the idea of potential energy. So this analogy is how much work. Well, it's not that big of a jump because, I mean, we are talking about energy, and energy is automatically work, right? So it's not a huge jump, but we'll think about it in a different way. Let's think about the idea of potential versus potential energy. When I put something up on a tall shelf, I talk about how much energy it will take me to lift it up to the shelf. Let's say the shelf is way up. It's 2 meters high. If I'm lifting 1 book up, and say that book is a kilogram, it's a big fat book, but it's a kilogram book, then I could talk about potential energy, mass, gravity, and the height of the shelf. These are independent from each other. If I decide to lift 2 books, maybe that's a big set of encyclopedias or something, so the next book also weighs that. I'm just doubling this. I'm not doubling the height. So the amount of stuff being lifted is different than how high the shelf is. They're independent of each other. So when I simply talk about potential, I would be talking only about the height. And in our case, instead of books and lifting them up physically, this would be the voltage. I'm still lifting things to the same height. It's still the same drop. It's just that now I'm having more electrons do it, not changing this voltage. And that's why we didn't double the voltage on that earlier problem.